All right, beautiful people. We're going to continue on with ratios and rates. We've already talked about a ratio being the relationship between two things or two numbers that represent different things. We've talked about how to solve the unit rate or solve for a unit rate, where you find the amount for one unit, whatever it is that you're studying. But now we're ready to use ratios and rates to solve problems. You know, in many ways, ratios look and behave like fractions. But you need to always note that ratios are not the same as fractions, because ratios can represent a part to whole or part to part relationship. Fractions represent part to whole relationships. You know, a fraction is a part of something, and ratios represent amounts of something that you have. Looking at module 6.3, we're starting on page 161. When we talk about how can you use ratios and rates to make comparisons and predictions. When we do these, we have to find equivalent ratios or rates with the same first and second terms, and then compare them to make the predictions. Now, first and second terms would be like the top and bottom. Sometimes we do that with the number line. Sometimes we do that with a table. And when we're comparing them with a table, it's kind of like a double number line. You can see here, like this would be one number line, this would be the other. But when we're using, I don't think that needs to be a little darker. That might be easier to see. Yeah, okay. When we're using the tables, remember what we said about equivalent ratios, how whatever you have as the multiplicative value, it's got to be the same for everything that you're working through. So if I'm comparing a recipe for lemonade where it's 2 parts of lemonade concentrate and 3 parts of water, and the other one is 3 cups of lemonade and 5 cups of water, for one, you have a 2-to-3 ratio. This is the lemon, this is the water. For the second one, you have a 3-to-5 relationship. That's the lemon, that's the water. Excuse me. But when you look at this, 3 is 2 more than, 3 is 1 more than 2. And in this one, 5 is 2 more than 3. So clearly they're not the same ratios, and that they're both in their simplest form. So if we're comparing them, what we want to look at is how they would be in terms of finding those commonalities. Now, if we look at Anna's recipe, we said already here that hers is 2 lemons to 3 waters. That's Anna's right there. So that's lemon to water, or 2-to-3. You could say 2-to-3 like that. Either way, it's the same, or you could use the word. And we know that Bailey's recipe was 3-to-5. So when you look at this and you make the comparison, we want to see which recipe makes the stronger lemonade. So what we want to do is extend the columns in our tables here. Hold on, I'm looking at something. Okay, we want to extend the columns where they have either the same amount of lemonade concentrate or the same amount of water. But basically, you want to do that so that we can see kind of where there are commonalities. So if we went through, remember the multiplicative value. On the top, here we have 2 times 2 is 4, 3 times 2 is 6. 3 times 3 is 9, 3 times 2 is 6. That's going to be 2 times 3. And this is going to be 2 times 5. 3 times 5 is 15. So 2 times 5 is 10. And if we look at those, we can stop there. Going across, with our concentrate and our water for Bailey's 3-to-5 ratio, we have 3 times 3 is 9, 5 times 3 is 15, 3 times 4 is 12, 5 times 4 is 20, that's 5 times 4, 5 times 5 is 25, so 3 times 5 is 15. Now, if you look at what we have, when you are looking at the table, we want to find two columns, one in each table, in which the amount of water is the same. So if you look at the water concentrates, here's 15 of water, and here's 15 of water. So I have for Bailey's recipe on the 15 water, it's 9 lemon to 15 water. And likewise, Anna's recipe is 10 to 15. Now I'm going to make this like it was a table. If I'm comparing Bailey's to Anna's, and you look at what they have based on the water, which one would have more of the lemon concentrate? That's right, Anna's would, because if you look here, she's going to have 10 with 15 cups of water, and she's going to have 9 with 15 cups of water. So Anna's is going to be the stronger lemonade. So I'm going to write that down. Stronger lemonade. Now, and that was just finding the common denominators. Everybody got that? And it's basically, when you look at them, it's just a comparison then. When you look at this, if we have Anna's is 10 over 15 right here, 10 over 15. So if we have Anna's recipe, it's Anna's, I'm going to put an A there. And if we take the 15 denominator, we have 9 over 15 for Bailey. 10 is greater than 9. So we're going to say that 10 fifteenths is greater than 9 fifteenths. And if we were to simplify that down, that would be the 2/3 and the 3/5. So this reduces to 2/3. This reduces to 3 goes into 9, 3 goes into 15, 5. So this is where we compare it. So that means that 2/3 is actually greater than 3/5. Anna's is stronger. So Anna's lemonade is stronger, the 2/3. So if we were to compare these ratios, like I just did, you've got the 10 fifteenths and the 9. 9 fifteenths is less than 10 fifteenths, so 10 fifteenths is greater, which means 2/3 would be greater than 3/5. Bada bing, bada boom. Okay. So in using the tables and comparing, kind of what they're doing and how those come together, you're looking for the similarities like you would in a fraction if you were finding a common factor. Only here we're finding a common term where you had the water the same in both. So 15 and 15. And because we have these the same, you can compare the ratios. It's like getting a common denominator. Now, in that way, it is kind of like a fraction, but we're still talking about the relationship between the water and the lemon concentrate, and that determines how strong the lemonade is, okay? Let's see. I'm going to look at this recipe. Let's see. Can you see that? There we go. In our recipe here, we're talking about comparing the ingredients. It says the fruit and nut bar calls for 4 cups of nuts, chopped nuts, 6 cups of fruit. So your nut to fruit ratio is 4 cups of fruit to 6 cups. Oh, wait, excuse me. That's backwards, Jennifer. 4 cups of nuts to 6 cups of fruit. And I just am labeling that right there. That's our nuts to fruit. So 4 to 6, that's another way to express it. If we look at the second person, Tanya, hers is 6 cups of nuts to 9 cups of fruit, 6 cups of nuts to 9 of fruit. Now, both of these can be simplified. If you look at what we have, and we look for equivalent ratios, I know that for 6 and 9, the common factor or the common denominator would be 18. 6 times 3 is 18, so 4 times 3 is 12. 9 times 2 is 18, and 6 times 2 is 12. So they both equal 12 eighteenths. So the ratios 4 6 and 6 ninths are equivalent. She used the same ratio in the recipe. Now, I want to show you another way. When you look at the common multiples and the ratios, you can kind of multiply up to get the common ratios, but in this instance, you could also simplify 4 6 and 6 ninths. 4 6 and 6 ninths have a common factor of 2. 2 goes into 4 2 times, 2 goes into 6 3 times, and 6 and 9 have 3 as a common factor. 3 goes into 6 2 times, and 3 goes into 9 3 times. So you have 2/3 and 2/3. So you can see, even though we know it's 12 eighteenths, if we simplified these, 2/3 of Tanya's is equal to 2/3 of the recipe. She just increased the amount. If you look at it, she just increased the amount that she's making. So one is going to be 10 cups and the other is going to be 15 cups. See how I did that? 4 plus 6 is 10, 6 plus 9 is 15. But the ratio of nuts to fruit is still 2 to 3, or 12 to 18 here if you went up. So that's pretty good, right? Let's look at that your turn question at the bottom, and let's map it out, because I think, let me open this up so I can write on it better. I think that being able to set it up and label what we're doing is going to be really helpful for what we're doing. If you look at this problem, this is at the bottom of page 162. In the science club, there are 2 6th graders for every 3 7th graders. At the science fair, there were 7 projects by 6th graders for every 12 projects by 7th graders. Is the ratio of 6th graders to 7th graders in the science club equivalent to the science fair projects by 6th graders to 7th graders? So if we look at it, if you think about the ratios, the 6th graders, you have 2 6th graders for every 3 7th graders. I can't do that with money, I'll do 2 6 to every 3 7th graders. So let's do this, 6th, and this is 7th. I hope you can see that. So with the 2 to 3 ratio of this and the ratio of the number of projects, it says they have 7 projects for every 12 projects, 7 for the 6th, 12 for the 7th. Now notice I'm keeping the 6th and the 7th different. If you look at these, I know 3 goes into 12, so I could make an equivalent fraction with that. Let's see, 3 times 4 is 12. So let's multiply 2 times 4. We're going to have 4 as our multiplicative value on both. 2 times 4 is 8. 3 times 4 is 12. Okay, there we go right there. Here is the projects. Here are the kids. So what do you think? Is it equivalent? Is 8/12 equal to 7/12? Remember, equivalent just means that they are equal. Is it? 8 is larger than 7ths, right? So here you have a higher concentration of 6th graders who are in the club than 6th graders who actually did the project. Does that make sense? So that would mean 8/12 is greater than 7/12. So the ratios are not equivalent. Let me make this neater. Ratio is not equivalent because we have, if we rename that, 2/3 equals 8/12. And we already know that we have the 7/12, and 8/12 is greater than 7/12. It's not a really greater than sign. 8/12 is greater than 7/12. I always like to have it where I can write down the items and have some of the topics and things where you can clearly see that the top represents 6th grade, the bottom represents 7th grade. Okay, let's talk about using rates to make predictions. Turn to the next page on 163. If you look at what we have here are two cities on the map. Janet drives from Clarkson to Humboldt in 2 hours. Suppose Janet drives for 10 hours. If she maintains the same driving rate, can she drive more than 600 miles? Justify your answer. Now, here's one where a table, or in this case, a double number line, will come in handy. We know that it takes her 2 hours to go from Clarkson to Humboldt. And we know that the distance from Clarkson to Humboldt is 112 miles. So she's going to go 112 miles in 2 hours. Does everybody see that? So what that means that is in 1 hour, she would go 56 miles. So 56 miles in 1 hour. I always like to solve for the unit rate right off. So 112 and 2, and it would be 56 miles in 1 hour, just so that we can see it. Now, if 56 miles is in 1 hour, we could take that 56 miles and multiply it by the 10 hours and see if she can get the 600 miles. So 56 times 10 is 560, thanks to the 0. And 560, if I look at that, and I'm comparing it to 600 miles, can she drive 600 miles in 10 hours? No, because 560 miles is as far as she can go. So when we look at this and we think about the ratio of the distance to the amount of time spent, if the distance covered in 1 hour is 56 miles, then the distance covered in 10 hours would be 560. And if I went along, this ratio for each interval can be simplified down to the 56 over 1 or the 112 over 2 because it's doubled each time. 2 times 2 is 4. 112 times 2 is 224. And so on. Times 3, times 3, times 4, times 4, times 5, times 5. So those are all equivalent ratios. It would take her at least 11 hours to go the 600 miles. This is in 10 hours, and this would be 10 plus hours. Okay? If we look at the relationship between her rate for 2 hours and the other rates that are shown on the number line, you see that all of these can be reduced down to this, or actually this, but that's not the simplest value. The 56 over 1 is the simplest value. So to find the equivalent rate, both terms, the miles, both the miles and the hours, I just abbreviated that, are multiplied by the same number. And I'll show you that. So here, 112 times 2 is 224. 2 times 2 is 4. 112 times 3 is 336. 2 times 3 is 6. 112 times 4 is 448. 2 times 4 is 8. 112 times 5 is 560. And 2 times 5 is 10. So you can see here that both the miles and the hours are multiplied by the same number as you go across to create that table, or in this case, this double number line. And really, a table is just another way to represent a number line. And we filled in the values on that. Can she drive 610 hours? We already said no, she can't. No, she only goes 560 miles in 10 hours. Okay? All right, very good. We're going to stop right there on this one. And I want to talk about ratios. I just want to kind of sum this up a little bit. When you talk about making equivalent ratios, remember that you're always going to take the top and the bottom number and multiply by the same multiplicative value. Or if you're dividing down to simplify, you're going to divide both the top and the bottom. Whatever you do to the top, you always do to the bottom. When we have equivalent ratios, or when we're checking for equivalent ratios, you take the two things that you're comparing, like the 5/6 on the oranges and the 2/3 on the apples to oranges. You take those, and then once you multiply through those, you are able to determine if they are equivalent. So we want to compare. We want to see if they're using the same. If I were to do this and fill in this table, 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. 6 times 2 is 12. 6 times 3 is 18. 6 times 4 is 24. Here, 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 3 times 2 is 6. 3 times 3 is 9. 3 times 8 is 24. Well, you can see here we have the common denominator of 24 on these. And we also have a common denominator of 6. So we could do either one and they would be the same. You could say that 5/6 compared to 4/6. 5/6 is obviously greater than 4/6. Or if we did the 24th, you could say 20/24 and 8/24. 20/24 is still greater than the 8/24. So when we look at this, Celeste is not using the correct ratio of apples to oranges because they're not equivalent. It would have to be something where she uses an equivalent ratio, like if she uses 5/6 and the other girl uses 15/8. Both of those ratios could be simplified down to the same value. Okay? Now, your assignment is going to be from page 165. You're going to do 6 through 14 even. Let me move this over here. So part of them are going to be on one side. You got a couple of multi-step problems, and then you're going to do down to the hot tamale questions on page 166. Remember to sort them out, label your parts. If you feel like you want to take it a little further, you can try the challenge problems. They're a little bit higher level thinking, but I think clearly if you are able to express your relationship and keep your units sorted out and organized, like if you're doing the money per tickets, you always are going to have the money in the numerator, tickets in the denominator, and so on. You should be able to sort it out and do pretty well with it. And after we do the book work, we'll do the online practice that goes with lesson 6.3. And I think that's it for that one. If I can figure out a way to stop it.